All right, new topic coming at you here in 6-4. It is split up into 2 days. Both lessons are relatively short. Want to take it nice and easy with both lessons because it's a new topic. It's a vector operation. It's called a dot product. And let's just dive right in to what that looks like. All right, so to do a dot product, you have two vectors. Let's call them u and v. You will see this written just like this. U dot v. Okay, you would take the first components and multiply them and add that to the product of the second components. Okay. Biggest thing I want you to keep in mind, because this is basically our third vector operation, we did scalar multiplication and vector addition that we did in section 3. Both of those, when you would perform them, your answer was a vector. We're going to stick with our fancy vector terminology. When you're doing the dot product, the answer is a scalar. Remember, that's in kind of the world of vectors, that's just a constant or a number, right? We saw that when it takes that name, a scalar, because when you multiply a vector by a scalar, it changes the magnitude. It's almost like a scale factor, which is why it gets referred to as a scalar. But the big thing here, when you take the dot product of two vectors, you don't get another vector, you just get a number. Got 3 examples to show you. Okay, so we got the first two components, 4 times 2, plus the product of the second 2, which would be 5 times 3. That would be 8 plus 15, which is 23. Okay, notice how it's just a number. Okay, and you can always go off of, if you're like getting an answer and you're thinking, is that a vector or a scalar? Pretty safe bet to go with if it involves 2 numbers, right? You're talking about a vector. If it's just that single number, that's a scalar. Now these other two, obviously the process of doing a dot product doesn't really vary, but I want to show you these other two for different reasons other than the process of just doing it. We get 2 plus negative 2, which is 0. That's actually a case that we'll look at more on the second day, but what I'm trying to show you here is that two vectors can have a dot product of 0. Okay, you saw in part A, it can obviously be a positive number. 0 times 4 plus 3 times negative 2. That would be negative 6. So there you see in the third part, a dot product can be negative. Okay? They can be positive, they can be 0, they can be negative. You've got an example showing each. This I don't want to spend a ton of time on. It's just on properties. Really 3 of them that I'd want you to kind of make note of. They're what you would call commutative. That's a fancy term for saying the order doesn't matter. If you were to flip the order of the dot product, you're still going to get the same thing. You take the dot product with the 0 vector, and it's just going to get 0. And then really this one right here we'll dive into in a minute. There's a relationship between, like if you take a vector and take the dot product with itself, that's related to that vector's magnitude. A few more examples that are a little fancier, I guess. They involve taking multiple dot products. Okay, so we're starting in the parentheses and we're saying, okay, do u dot v. Well, all right then. U dot v would be negative 1 times 2 plus 3 times negative 4. Now don't forget, out here on the outside, This is saying, hey, once you're done with that, also do, multiply that by W. Now here this gets interesting because in here, U dot V, you should be expecting to get an answer that is a scalar, okay, which is exactly where we're headed. Basically, negative 2 minus 12, that dot product is negative 14, and now we're going to multiply that by vector W, which is 1, negative 2. So now this is basically scalar multiplication, as I multiply both of those terms by negative 14. And there you go. Okay, so notice there that problem involved a dot product, but then we took that answer, which was negative 14, and we multiplied it by a vector, and we ended up getting a vector here for our final answer. Okay, the issue here being that we did more than just a dot product. Okay, we took that answer from the dot product and then multiplied it by that vector. All right, so here we'll do U dot, let's get 2V. That's just scalar multiplication there. So I take both components of V and I doubled them. Okay, now we do have a dot product. This is going to be negative 1, 3. There's vector U dot 4, negative 8. Which would be negative 1 times 4 plus 3 times negative 8, negative 4 minus 24, and negative 28. Okay, there we ended up getting a scalar as our answer. All right. When you're practicing these problems, be sure to check in the back of the book if they're odd, if you're, because they can vary. Dot products give you a scalar as an answer, but if there's more going on in the problem, you might get a vector as an answer, you might get a scalar. You can be assured you're going to get one of those two. All right, here is a quick example that I want to do. Last one of day one. Okay, we're not going to, you'll see the next slide gets into the angle formed by two vectors. That's a day 2 topic. Okay. If you take a dot product of a vector with itself, things get a little interesting. It says it's the magnitude of the vector squared. We're going to prove this, and it's not going to take long to do. All right, so V dot V, keeping in mind down here, for any vector, assuming it's in component form, its magnitude is v1 squared plus v2 squared square root. Okay, that's a vector's magnitude. So now if I start to think about magnitude squared, then I'm just thinking, all right, that's v1 squared plus v2 squared, right? No square root. So this would be v1 times v1 plus v2 times v2, right? The only difference here is, if you look back to your original definition, you would see u1 times v1. There's no u, right? It's vector v dot product with vector v. Well, there's v1 squared plus v2 squared, and if I'm not mistaken, I do believe this is the exact same thing as that, which would mean this is the same as that. Okay? So it tells us that the dot for this vector u, it doesn't give us the vector, but it just says the dot product with itself is 5. What is its magnitude? Okay? Well, that would mean that u dot u is 5, and this formula that we've just proven tells us that 5 would be the vector's magnitude squared. Simple little step. Just take the square root, and I can tell you that vector u, its magnitude is the square root of 5.